Okay, so like I said, we're going to be looking at section 3.5 today. So we've practiced how to graph lines so far. We've practiced how to graph parabolas or quadratic functions. We've even practiced how to find all the pieces to a polynomial, and so today we're going to talk about a different type of function called a rational function. So first, let's make sure we know what a rational function is. A rational function is basically just the quotient of two polynomial functions. Or it's basically a fraction with x in the denominator. Okay, those are two kind of different ways to think of them. Really the same, but. So although we haven't specifically mentioned rational functions this semester, we did talk about them when we talked about domain. So remember how I asked you to find the domain of this guy? This was actually on test 1 or one like it. Okay, and of course, if I ask you to find the domain, what's the off-limits value for x? Like what isn't allowed to happen? X can't be 3, right? So x can't be 3, so the domain we would say was negative infinity to 3, right? Not including 3, and then 3 to infinity. So this is a rational function, right? Because it's a fraction with x in the denominator. Okay, so we're going to be dealing with rational functions that look like this, but maybe that look a little bit differently also. All right, so there are some distinct parts of rational function graphs that maybe didn't show up with polynomial graphs. So first let's talk about what a vertical asymptote is. I'm going to abbreviate that for the rest of the notes as VA. Okay. A vertical asymptote is a vertical boundary line that the graph approaches but doesn't touch or cross. When I say approaches, I mean it gets super, super close to the line without actually touching or crossing. Kind of like if you're babysitting and you tell a kid, hey, don't come over here, don't cross this line. They always want to get right up to it. That's kind of what vertical asymptotes are. They're going to get as close as they can to it without actually touching or crossing it. All right, so let's talk about how to find vertical asymptotes. So to find vertical asymptotes, first you're going to simplify the rational function. And then you're going to set the denominator to 0. Okay, so it turns out that wherever your off-limits values of the domain are, then that's where the asymptotes show up. So if we were asked to sketch a graph of the function that I just mentioned, so without getting too detailed, because we're going to get very detailed with what these graphs look like. So let's say I asked you to graph that 3 over x minus 3 that I mentioned. Now, what did we already say that the graph wasn't going to be, or the x wasn't going to be allowed to be? X can't be 3. So what happens is we usually show the asymptote or the off-limits boundary line with like a dashed line, meaning that it's not part of the graph, it's an off-limits portion of the graph. And then this is what this graph actually looks like. It has a curve right here, and it has a curve right here as well. Okay, so that's what the graph of 3 over x minus 3 looks like, and we're going to practice being able to graph that by hand, okay? However, let's glance, while you're kind of catching up with that, let's glance at what the calculator is going to show. Now, it kind of depends on what kind of calculator you use. If you have an 84 or above, it's going to look like mine here. So notice that when I put it in the calculator, I have to put parentheses around the bottom because x minus 3 is the entire parentheses. So I've said this a couple times this semester, but remember, anything with more than one part, put a parentheses around it, okay? So notice it's going to show us a very similar graph to what we just sketched, but what does it not kind of show at all? It doesn't really show that dashed line, right, that asymptote, but can you see that it's still avoiding it even though it's not technically showing it as a dashed line, okay? The 83s and before actually show them as solid lines, which I think is actually even worse than not showing it at all. Does anybody have an 83? I don't think anybody does. I should have brought one, but I don't think I even have one in my office. But the 83s, unfortunately, show it as a line, and so what it can look like is, you don't need to draw this, just be aware if you have an 83, it'll show it like this, but like a lot of people will think it's actually part of the graph, and it's not, okay? So this is actually not really part of the graph, right? It's just the boundary line the graph is getting super, super close to, so you have to be a little cautious about that. Okay, so let's look at some more, but before we do, just know that most rational function graphs have more than one piece like this graph did. And the reason they're going to have more than one piece is because they're going to have asymptotes, breaking them up. Asymptote pieces where we're skipping over those points. Okay, so let's, instead of sketching the graphs right off the bat, let's just practice finding the vertical asymptotes for a couple of functions. I want you to find the vertical asymptote slash asymptotes of the following. So g of x equals x plus 5 over x squared minus 3x. So the first thing that you would do is factor this to see if it can be simplified at all. So how could I factor the bottom? What does x squared and 3x have in common? X, right? So if I pull out an x, I'll have x minus 3. Okay, notice nothing can be canceled or anything like that. Okay, so it turns out that we're going to set the denominator that we just factored equal to 0. So that means we have a vertical asymptote at x equals 0, and where else? If you set x minus 3 equal to 0, what do you get? 3? Okay, so you just set each of those parts equal to 0. So the very spots where the off-limits values would be is actually where there would be asymptotes. Okay. So if we have two vertical asymptotes, think about that. How many pieces should the graph be in if there are two boundary lines the graph's not going to cross? If there are two pieces when there's one asymptote, how many do you think there'll be for two? There'll be like 3 sections, right? One on the left, one on the right, and then one in between the two. Okay. So we might graph one like that in just a minute, but for now I just kind of want you to visualize what that looks like. So what about this one? Find the vertical asymptotes for h of x equals x minus 4 over x squared plus 5x plus 6. So the first thing you need to do is factor slash simplify. Okay, so remember you can pull out your AC method, or you can realize that I just have a coefficient in front of x squared, that's 1. So maybe it'd be easier just to think about what are the factors of 6 that add up to what? Add up to 5. So what are the factors of 6 that add up to positive 5? 3 and 2, right? So notice this is what this one factors into. So again, notice there's nothing that can be done simplification-wise, right? Nothing cancels out, okay? So then you're going to set that denominator equal to 0. So your vertical asymptotes are going to be at x equals -2 and at x equals -3. Okay, if you need to show the step where you actually set x plus 2 equal to 0 and subtract 2 from both sides, and then x plus 3 equal to 0 and subtract 3 from both sides, then you can feel free to do that too. Okay, so let's do one more, and then we're going to stop and talk about what we get here. So find the vertical asymptote, or possibly plural, for the following function. For f of x equals 2x plus 4 over x squared plus 3x plus 2. So notice I'm not giving you crazy things to factor, and you'll probably notice that on your homework too, but you do have to know how to do basic factoring. That's why we cover it during the first week in review. I'm just expecting at this point in the semester that you already know how to factor both the top and the bottom, because by the way, the top will factor a bit too, right? What do you notice the top has in common? A 2, so if we factor that out, we get x plus 2. And then what about the bottom? What are the factors of 2 that add up to 3? 2 and 1, right? Because 2 plus 1 is 3. So different from the previous 2, what do you notice here? What could I go ahead and actually get rid of or simplify? I could get rid of that. We're going to talk about what we did there in just a minute. But that means that now we just set what equal to 0? X plus 1. So we actually only have a single vertical asymptote at negative 1. Okay. But just so you know, up here, I'm going to write this in another color. Anything that gets canceled out here represents a hole in the graph. Okay, so what that means for us is there's actually a hole in the graph where we canceled at x equals negative 2. Okay, so I'm not going to focus too much on that, but I did want to mention it, okay, because I want us to take a look at the graph when you're finished writing that down. So notice if I want to punch this in, I need to do parentheses around the top and the bottom. Remember, anything with more than one piece, put a parentheses around it. So it's 2x plus 4 on the top, and it's x squared plus 3x plus 2 on the bottom. Okay, so when you look at this graph, it shouldn't be any real shocker to you. It only has one vertical asymptote. Where does it look like it is, just like we found? At negative 1, right? It looks like it's avoiding that x equals negative 1 line, okay? But if you go and look at the table, I don't know if you've ever done that, but if you go second graph, notice that there's an error both at negative 2 and at negative 1. Negative 2 because there's an asymptote, or sorry, negative 1 because there's an asymptote, but why is there an error at negative 2? Because there's actually a hole there, okay? So just so you know what it actually looks like, but your calculator is unable to show this to you, what it actually looks like is there's actually a hole right here. So remember how you sometimes see graphs that don't look like they're continuous and you wonder why? This is where the hole shows up. Okay, but the calculator doesn't have enough pixels basically to show you that. Okay, so just know that if you cancel something out, it does actually represent a hole. So, but again, I'm not going to focus too heavily on that. I really want you to know asymptotes better than the holes in the graph necessarily. Okay, so let's look at one more, and then we're going to switch to another kind of asymptote we can have in our graphs. So find the vertical asymptote, or possibly plural asymptotes, for x over x squared plus 3. So what are you supposed to do first? You're supposed to simplify / factor, right? Notice there's really not anything that you can do here though, right? These don't have anything in common. Okay, so I'm just going to write this here. This can't factor or simplify. So when you can't factor or simplify, you just try to set the denominator equal to 0. So if there's nothing you can do, you're just going to set x squared plus 3 equal to 0. And then let's follow that through and talk about what that means, right? So we're going to subtract 3 from both sides. So we're going to get x squared equals negative 3. And then when I try to go take the square root of both sides, which is what I should do next, so I'm going to rewrite this here so that I show both steps. What's the problem with me taking the square root of both sides? Don't forget the plus and minus. What kind of answer am I going to get here? Imaginary? So what that actually means is there's no value of x that is a real number that's going to make the denominator 0. Okay? So I'm going to kind of write this over here. So no real number x makes the denominator 0. So what do you think that means? Yeah, there's none. Okay, there is no vertical asymptote. Okay, if you can't make the denominator 0 even after simplifying, then it means there wasn't a vertical asymptote to begin with. So if you were to look at that graph, you wouldn't find a space where it looks like it's getting close to without actually crossing. Okay, so what are the 2 steps for vertical asymptotes before we move on to a different kind of asymptote? What are the 2 steps? First, you simplify if possible, right? And then you set the denominator equal to what? 0. And anything that makes the denominator 0, you'll say x equals that number would be the vertical asymptote. Okay, make sure that you write it as x equals because it's a vertical line, so it doesn't need to just be 3. It needs to be x equals 3. Okay, so we can also have horizontal asymptotes. These are different, not just in the fact that they're obviously going to be horizontal, but they actually work a little different than vertical asymptotes also. So I am going to abbreviate those as HAs. So here is how they are different. It's a horizontal boundary line. That the graph approaches. But here's what makes it different from a vertical asymptote other than the direction. It's only at the far left and the far right. So if you ever take a calculus class, you'll go into a lot more detail here. Okay, I'm not going to do that because obviously this isn't a calculus class, but just know that the horizontal asymptotes only have to follow the rules on the far left of the graph and the far right. They don't have to follow the rules in the middle, and we're going to look at an example of what I mean by that here in a minute. So for horizontal asymptotes, there are really not a whole lot of work to show for them, but there are 3 possibilities / cases for what you can expect for horizontal asymptotes. Okay, and it all has to do with the power on top versus the power on bottom. So let's get to the 3 cases. So if the degree, in other words the power, of the numerator is bigger than the degree of the denominator, then there's no horizontal asymptote at all. So if you have like a 4th power over a 3rd power, if you have a 5th power over a 1st power, anything where the top power is bigger than the bottom power, then there's not going to be any horizontal asymptote at all. What if the opposite is true? So what if the degree of the numerator is smaller than the degree of the denominator? If that happens, then the horizontal asymptote is y equals 0. And notice that we write vertical asymptotes as x equals a number, and then we write horizontal asymptotes as y equals a number. By the way, that's how we write vertical and horizontal lines in general. Vertical lines are x equals some number, horizontal lines are y equals some number. So I've covered if the degree on top is bigger or if it's smaller, right? What have I not covered then? Yeah, what if they're the same? So that's the third case. So if the degrees of the numerator and denominators are the same as each other, then basically you just pull the leading coefficient from the top over the leading coefficient for the bottom. So the horizontal asymptote will be y equals leading coefficient of the top over leading coefficient of the bottom. Okay, so that's going to be easier to find than it sounds. It's just going to be pulling one number from the top, putting it over one number from the bottom. Okay, so let's do maybe like a three-parter here. So I don't want you to do anything other than find the horizontal asymptote of the following three equations, and we're just going to write them all at once. So the first one looks like this. Second one looks like this. Actually, I think we're going to do 4 of these. Third one looks like this. And lastly, last one looks like this. Let me slide that up. So what if I didn't, but what if I had asked you to find vertical asymptotes of all of these? You would simplify and then set the what? Denominator to 0, right? But I didn't ask you that. I asked you for horizontal asymptotes, okay? And remember, you just have to compare the powers on top versus the powers on bottom. So what do you notice about the power on top here? Yeah, the power on top is bigger. So when the power on top is bigger, what do we say? No. Yeah, none. Okay, so on my lab, on your homework, there'll be a multiple choice option for you to pick none. Okay, what do you notice on part B? What do you notice about the powers? Yeah, the powers are the same. So that means it is going to have a horizontal asymptote. It's going to be y equals something, because it has to be y equals something. Okay? And to find out what it is, you just pull the leading coefficient on the top, right? What's the understood number in front of x squared, since I didn't write one? 1. So you just pull this number over that number. Okay, so it's literally as easy as that. And it doesn't matter where you put the negative, but it'd be 1 over -3 or just -1/3. So there's a horizontal boundary line at -1/3. That's what that means. Okay, what about C? Power on top is what? Smaller. So the horizontal asymptote is what? Y equals 0. and then last but not least, what do you notice about the powers on the bottom? Now, I did kind of switch them to see if you were paying attention, right? It's not just the first thing that's listed, it's the highest power thing that's listed. So what do you actually notice? Yeah, the powers are the same again. So remember, leading coefficient doesn't necessarily mean the one you start with. It means the number in front of the highest exponent thing. So it would actually be y equals what? 2 over 5. Okay, and again, you have to have the y equals part. Okay, so vertical asymptotes, you just set the denominator to 0 once you simplify. Horizontal asymptotes, there's not really much work to show other than comparing the powers of the top and the powers of the bottom. Okay, so we're going to get to graphing some of these on our own, but I want you to kind of quickly try to sketch a graph with me, and I want you to try to find all the asymptotes. So let's say we just need to go out maybe 3 in every direction. And then let's say that we are going to have a boundary line here, here, and then here. Okay, so notice I'm showing with dashed lines where the boundaries are. And then let's say my graph ends up looking something like this. It has a curve there, it has a curve down to the left, but then the piece in the middle kind of ends up looking like this. And let's make that not actually touch the line there. It's supposed to just get super close without actually touching it. Now, note, like, for me to get you to graph the same graph that I have up here, I kind of had to draw the dashed lines. Some of the ones you see on your homework, though, you won't see the dashed lines. You'll just see a gap, and you're going to have to recognize where that gap is. So, but looking at this graph, how many vertical asymptotes does it look like we have? 2, right? One at -3. Notice I'm writing x equals, right? And then another one at what? At 1. Okay, and then for horizontal asymptotes, okay, first thing is before we say what we have, notice that we look like we have one, but the middle piece is crossing through it, which remember is not technically supposed to do. However, what did we say about horizontal asymptotes? They only have to follow the rules at what? The far left, which is this curve, and the far right, which is this curve. In other words, in the middle, it can kind of do what it wants, okay? It can cross through. So that is still a horizontal asymptote. Just think of the middle pieces of the graphs as kind of rule breakers. They don't necessarily have to follow the rules with horizontal asymptotes. Okay, they do have to follow the rules with vertical asymptotes. So they won't cross the vertical asymptote, but they could possibly cross the horizontal asymptote like this one did right here. Okay, so remember when we talked about polynomial functions, remember those were the curvy functions that could be like third power, fourth power, or whatever. We talked about how to find pieces of the graph, and then we put them all together in order to tell what the graph looked like. Okay, so that's similar to what we're going to do here. So there are 6 steps for graphing rational functions. I'm going to walk you through them, but a lot of them we already know how to do because we've done them with other types of functions before. Just know that on your homework, it's going to walk you through all these stages as well. Okay. So the first step is, I'm not going to spend a lot of time on this, but determine if there is symmetry or not. Remember, we did this with polynomials too. It's just that if you know it has symmetry, remember it can help you kind of know what the graph is. So remember, even means there's y-axis symmetry. If it's odd, there's origin symmetry. Most often, it's going to be neither, and what is that going to tell us? There's, yeah, neither of those types of symmetry, okay? So just to jog your memory, remember to tell even, odd, or neither, you're supposed to be replacing x with negative x and comparing. Again, I'm not going to focus or worry too much about this, but it is a step that's on my lab, so I wanted to make sure and include it in the notes here. All right, so step 2, but really the first real step that I care about is finding the y-intercept. Okay, we've done that a bunch of different times every time we've talked about a new graph for a type of function, right? How do you always find the y-intercept no matter what we're talking about? Yeah, set x to 0. Okay, and then you're going to find any x-intercepts. Remember, there can only be one y-intercept, but there could be more than one x-intercepts. How do we do that again? The other one, right? Y equal to 0. Okay. By the way, here's a little helpful hint here. Really, if you're setting y equal to 0, you really just care about when the numerator is 0. Since 0 over anything is just 0. We'll look at an example of it in a minute. But if you want to find out when a fraction is 0, you really just need to focus on the top being 0. By the way, what can't be 0 at all? The denominator is what can't be 0, right? So if you make the top 0, then a fraction is valued at 0. Number 4 is you need to find the vertical asymptote or asymptotes. Okay, how do we do that again? Simplify, then what? Then set the denominator to 0. That's what we just learned today. Step number 5 is you're going to find the horizontal asymptote, if any. Okay, so your quick reminder here is 3 cases. It's either none, 0, or it's top number or bottom number. And then last but not least, just like we did with polynomial graphs, you're going to graph all the info you have, and you're going to pick additional points if you think you need them. Okay, but just like polynomial graphs, how are you going to know where your gaps are? You can't know where your gaps are until you've done what? Graph the things that you do know, right? So you graph the things you do know and you see, like, where do I still not really know what the graph is doing, okay? Just to let you know, my lab usually picks points for you. But on test 2, you're going to need to be able to pick your own points. Okay, based on, where the gaps are. Okay, so we're going to start off a little with a little basic rational graph, and then we'll get more complicated as we go. So what if I asked you to run through all the steps of graphing 1 over x minus 1? So first thing is, how come we know this is a rational graph? Because it is for sure. How do we know that? Because where is the x located? It's in a fraction, and it's where? In the denominator of the fraction. Okay. All right, so let's run through all the steps. So the first step, remember, is to figure out if we have any symmetry or not. So it'll be a good review anyway. So what we basically do is plug in negative x everywhere we find an x. But notice this doesn't give you the negative version, right? So this is neither. So what does this tell us about symmetry? No symmetry. Okay. Number 2, we need to find the y-intercept. Okay. Don't make that harder than it is. It's really easy to find. How do we find the y-intercept always? Plug in 0 for x, right? So 1 over 0 minus 1. So you're just going to get 1 over negative 1 or negative 1. Okay. okay? I'm pretty sure that MyLab wants you to enter that as a point, so we would plot that as the point 0, comma, negative 1. What's step number 3? So I took the steps off, but you should still have them. Yes. Step number 3 is to find any and all x-intercepts. Remember, we just set y equal to 0. Okay, however, remember what I said, you actually would set the numerator equal to 0, but what do you notice? The numerator cannot be 0, because what's the numerator set at, no matter what x is? The numerator is the number what every time? 1, right? It can't be 0, okay? So if you can't set the numerator equal to 0, then what do you think that means? There's no x-intercept, that's what it means. Okay, so what does it never ever do when we graph this thing? Never touches the x-axis, okay? Step number 4 is to find any vertical asymptotes. So let me write the equation again. Right, so what do? Simplify, then set the denominator to 0, right? But that's easy to do, right? So what would be x minus 1 equal to 0? So what would we get? X equals 1, right? So there's a vertical boundary line at 1. So last step before we get to the graphing part. Okay, so if you look at the horizontal asymptote, what are you supposed to be comparing? The power on top versus the power on bottom. Okay, notice there isn't even an x at all on the top. There's not even a power. So the power on top is smaller because it's actually 0. So when the power on top is smaller, what does it mean about the horizontal asymptote? So you might need to look back at your steps. But the horizontal asymptote is 0 when the power on top is smaller. When the power on top is bigger, remember, it's none. Okay, so step number 6 is the mother of all the steps we're doing here. This is like what we're trying to get to. We're going to see if we have enough info. So I don't really need to count very big. So maybe I'll just go out like 3 in every direction. But then you just start at the top and start working your way through the information you know, right? So we don't know anything from step 1 since there was no symmetry. We know it crosses the y-axis at -1. It doesn't even have an x-intercept, right? It has a vertical asymptote at 1, so you're going to draw like a dashed line, right, indicating that the graph's going to get close to that without crossing it. And then we have a horizontal asymptote at 0. So can you see that like we don't have near enough info here, right? We only have actually how many points total? We only know 1 point, but we do have some boundaries that the graph's going to get super close to, okay? So really important on the test that you know how to pick the additional points. And my suggestion to you is you can pick as many as you want. Remember I told you MyLab's going to pick quite a few for you, okay, and make you plug them in. But I would just pick, like, make sure you have a couple of points on either side of the asymptotes, right? So notice I know what 0 is, right? So maybe I'd like to know what -1 is, too. If I had -1, then I might be able to work with that. But then what about on the right side over here? You don't have anything over here, right? So what could you maybe pick? Maybe 2 and 3? Okay, so I didn't pick 2 on the left because I had 1 point already, but I went ahead and picked 2 on the right, okay? And I'm just going to say this, pick more if needed. So if you are doing this on your own and you're like, I still don't feel confident that I know what the graph looks like, you can pick as many x points as you want to, okay? And how do you deal with these then? Plug these in. Okay, so my strong suggestion to you is to use your calculator, but you can use your calculator like the table feature of your calculator, or you can just plug them in to the actual calculator part. My battery's running low. So notice, if you plug in -1, you're going to get 1 over -1 minus 1. Hang on, I didn't enter that in right. So you get -1/2. So the next one, let's plug in 2. So 1 over 2 minus 1. Some of these you might not need a calculator for. You get 1. And then let's plug in 3. And notice I'm going to get 1/2. Okay, so let's graph those points and see if it's enough for me to be able to tell what's going on with the graph. So at -1, I am at -1/2, so maybe about here-ish. So I don't know about you, but I think that's enough for me to tell that the graph's going to like slide this way and this way. Like we know it has to scoot close to the asymptotes, it just doesn't cross them, right? So I think that's enough. On this other side, we have 2, 1, and then we have 3/2. And again, I think that's enough to know that, hey, we're going to get super close here, and then we're going to curve and get super close up here. Okay? But what if you think that you wouldn't know what that graph looked like? What could you always do? Pick more x's if you wanted to, right? So my general rule is I want to see at least a couple points on each side. If you want to pick more than that, then feel free to do that. Okay? So that needs to kind of be your general rule of thumb. Pick a couple points in each little section, and then you should be able to usually tell what the graph is. If not, you're going to pick more points. Okay, so let's look at another one. By the way, before we look at the next one, you will not have to memorize step 1, step 2, step 3 for the test. Okay, what I would do on a test, I told you I would do something very similar for polynomial graphs, is I'll say graph this thing by giving me or showing me all the steps to find blah, 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 blah. And I'll list the things I want you to find. So you have to know how to do each individual step, but you don't have to remember like which part was step 1, which part was step 4. You don't have to do any of that. Okay? But the individual steps, you're still going to need to make sure you know how to do them on their own. So graph g of x equals 3x minus 1 over x plus 3. So I might even run through these a little bit quicker than last time. So step 1 is just to find out if there's symmetry. Remember, you do that by plugging in negative x everywhere there's an x. Okay, I'm going to skip ahead. This has neither. Like if you plug in negative x for both x's, you're not going to get either the same thing or the negative version of the original. So I don't really like to spend a whole lot of time on symmetry. It helps rarely, so I don't worry too much about that step. All right, but y-intercept, I do want to find that. So what do I do for that again? Set x to 0, right? So just find g of 0. So everywhere there's an x, plug in a 0. So you end up getting negative 1/3. Okay, remember MyLab's going to want you to write that as a point. So you would say 0, comma negative 1/3. Okay, so what's step 3 if step 2 is the y-intercept? X-intercept, I meant to say x, but I wrote y again. Okay, so remember for this one, you just set the numerator equal to 0. So you just say, okay, 3x minus 1 equals 0. And if you solve by adding 1 and dividing by 3, you're going to get 1/3. So what point is that? It's not 0, 1/3, but it's going to be the opposite, right? 1/3, comma 0, if you write it as a point. Step 4 is to find the vertical asymptote, if any. Okay, so what do you notice about the function? It's already simplified, right? So 3x minus 1 over x plus 3 can't be simplified, so I just need to set what? The denominator to 0, and I get x equals negative 3. So lastly, before I get to the graphing part, okay, I've got horizontal asymptotes. Remember, this is where I have 3 cases comparing powers on top to powers on bottom. Okay, so what do you notice about the powers? It's not on screen anymore, actually it is right here. What do you notice about the powers in both of these? Powers are the same. So the horizontal asymptote is y equals what? 3 over 1 or just y equals 3? So all of this stuff, I'm going to do step 6 up over here. All of this stuff is going to get combined, and I'm going to see if I can come up with a decent look for what the graph is. So I'm going to go out to just 3 again, but if I need to go bigger, you can just extend the graph out a bit. And just go through your list and start marking stuff, right? It crosses the y-axis at -1/3, so maybe about right here-ish. But the x-axis it crosses at 1/3, so maybe about right there. There's a vertical asymptote at -3, and there's a horizontal asymptote at 3. So honestly, I think this side is good enough. Like, I think I can go ahead and just curve it and scoot it close to the asymptotes. You could pick more points if you really wanted to, okay? But what do I not know anything about, really? Yeah, I really just don't know what's going on over here, right? So when you go to pick additional points, you have to pick where the points are that you're not sure about. Okay, so again, MyLab's going to pick these for you, but on the test, you got to be able to pick them on your own. Okay, so I have an asymptote at -3, but I'd really probably like to know what's going on over here. So maybe at what 2 points would I like to pick then? -4 and maybe -5. Okay, and remember, you're just going to let your calculator do all the mess, right? You're just going to punch everything into your calculator to see what you get. Just make sure when you use your calculator that you do parentheses around the top and parentheses around the bottom, okay? So to save time, I'm going to tell you what you get here. You get 13 for this one, and you get 8 for this one. Okay, so do you remember what we did when we got really big numbers with our polynomial graphs? Did I make you count up to 13 or numbers that large? No, okay. So I think we could probably count up to 8. So let's go ahead and do that, and then we're just going to kind of fudge this one. So 4, 5, 6, 7, 8 could be here, right? Remember, that's 5, -5, 8. So for -413, if you want, you can just do something like this. You can just say, okay, all the way up here, I don't feel like counting it. I'm just going to write it like that. And then you have -413, right? But then still make sure that you curve it, right? So notice it's got to stay within those boundary lines. So what if 2 points weren't enough for you? Then you would choose what? More points if needed, right? So pick more if you think you need it. But notice I only picked 2 this time because I already had 2 that were pretty solid, whereas the first example I only had 1 point period. That's all I had.